Assalamu alaikum. In today's lecture, we are going to find the electric field intensity of a long straight line. The actual goal of this series of lectures starting from today is to find the capacitance of a transmission line. And in order to find the capacitance C, we should know the potential difference. Why? Because we know that Q is equal to CV. So if we know voltage, we can find the capacitance. And in order to calculate the voltage, we should know electric field intensity. So in today's lecture, we are going to find the electric field intensity of a long straight line, which is actually the overhead conductor. As a starting point, we are considering a cylinder, which is the representation of a conductor, and we know that the charge is displaced over the conductor, so there is no electric field inside the conductor. It is radially outward from the conductor as the charge is placed over the conductor. So in order to calculate the electric field at a certain distance from the conductor, we have to first define a surface that is covering the whole conductor, and this surface is known as Gaussian surface, which is at a distance x from the conductor. So as the charge is displaced over the conductor, then the electric field lines are radially outward, so this electric field value will be constant over this surface, or at this surface the electric field value will be constant. So what is this surface? This is a Gaussian surface, which is actually defined based on the Gaussian law, and the Gaussian law actually states that the total charge that is actually enclosed in a surface is proportional to the flux through the surface. So the flux through that surface is actually giving you the idea that how much charge is enclosed by that surface, and the surface is known as Gaussian surface. And if I have to write the Gaussian law mathematically, that is actually the closed integral of electric field intensity, which is actually equal to the charge enclosed divided by the permittivity value K0. In some book we also have the notation epsilon naught, so this is the permittivity. And permittivity actually is the ability of a substance to store electrical energy in its electrical field. So the Gaussian law states that the closed integral of electric field intensity is equal to the charge enclosed by the closed surface, which is the Gaussian surface. And this charge enclosed is the same charge that is just placed over the surface of the conductor. And if I say the value of the charge is Q coulomb per meter, so it will be replaced by Q enclosed in this formula. So as the distance from the conductor is x, which is equidistance, so the value of E over this line will be constant. So we can take this E outside the integral because this is a constant value. So when we will bring it out, this is the closed integral dA, which will give you the surface area, and the surface area of the cylinder is 2 pi RL. And in this case, the cylinder, the Gaussian surface cylinder, is actually at a distance x, so we will replace this R with x. So this is 2 pi XL. So this value is actually 2 pi XL. So electric field intensity is actually equal to Q over K naught 2 pi XL volt per meter. Now in this formula we have the variable for length, but usually we calculate the electric field intensity in per unit length, so therefore this length will be equal to 1, and in the final formula we will have volt per meter. So this L, when replaced by 1, make the formula E is equal to Q over 2 pi x K naught, and here K naught is the permittivity. As I have mentioned before, this is permittivity, but the actual value of permittivity is K naught into Kr, where Kr is relative permittivity and K naught is the permittivity of the vacuum. So the relative permittivity value is 1.00054, which is approximately equal to 1, and the value of K naught is 8.85 into 10 raised to minus 12 farad per meter. So this is the formula for electric field intensity that you will use in order to calculate the potential difference. 2 pi kx, where k will be replaced by K naught if k is equal to 1. Thank you.